All right, welcome back, everyone. Again, I apologize about the video not picking up the audio from last time. Hope that's the last time that happens. So I've got a couple of things for you. I will call your name, and if you could come up here, grab this real quick. Augustine, Mr. Ruiz, Isiero, no, I can't say his name. I can't do it. Elizabeth Centeno, Margie Ortiz, Tien Lu, Kiki, no Kiki, all right. Jared, gonna be right here, Jared. Ernesto, Chris B, Ishmael, did you pick up that book? Alexis, Sean, Christian, hey, Eddie Garcia, Elizabeth, must have scared a bunch of people away. Naomi, Fiora, oh wait, Fiori, okay. Alejandro, Mr. Tuck, Chris Juarez, Felicia, Christy, Samantha, Jennifer Ferris, Kieran, where? Okay, heard your voice. I couldn't tell where it came from. All right, make sure you get your clicker. I know with this terrible weather, it's very difficult to navigate through the streets. Okay, look, if you just came in, come up here, get your clicker, and then over here, try and find your name on these lists. It's highlighted. Your name is highlighted. Make sure you pick your name off that. You didn't do it? When? Really? Huh. Weird. I'll have to look into that. I don't know why you wouldn't be on there now. It's very odd. You sure you were on the first one? If you have time after class, I'll show you what my records show online of who's done it. Because that's a quiz grade. I don't want you to get a 0 if you did it. Sure. We believe you. I know, right? It's the easiest 100 you're going to get in this class. The bonus has been collected. Last call, bonus. Make sure your answer is boxed so I can see. Homework I don't collect. The bonus question, yes. Name. Are we going to talk, Sean? Let's talk. You have time after class? All right, let's talk. Thank you. Okay, everybody has their clicker, right? Everyone has their clicker. Thank you. Is that a bonus question? Okay. Make sure you get your clicker. What's your name, sir, again? Here you go. Are we ready for attendance? Okay, go ahead. Alejandro, what happened? What was that? Oh, if you press it more than once, it does that, or what? Oh, press a different number, it comes up different? Okay. Just press 1. Everyone good? All right. All right, so let me explain what I handed out to you. I compiled all of the students' schedules. I had 25 of 26, but apparently there's something wrong. Okay, I'm not going to redo this, and this is the final version of it. I've gone through every single student in here, and I've highlighted your name. Do you have yours? Yeah. What's your name? Oh, here. Sorry. Did you have one? Did you do a survey online? You did? Oh, there. Elizabeth? Okay. Who else? All right. So if you look across, I realize this just looks like a huge mess, all right? But the darker bars across are when I'm in my office, okay? So if you put OK at a time that I'm in my office, I actually highlighted it in yellow. And that shows exactly when it is that you say you're going to study for this class and I say I'm going to be in my office, which means you can come by and get help. Now, if you are a student who your hours don't match my office hours, then you have a red X in the top left-hand corner of your page. I believe there's only like 4 people in the class that have complete opposite schedules than I do. Everyone else has at least 1 hour out of the week that you could come get help, right? And then the rest of it is just so you can go and look, when your classmates are free and maybe y'all can get together. I leave that up to you. All right, I could tell there was a pretty big group came in here together. Do y'all study together? Okay, so there's already a big group. Maybe we can get a couple of groups going in here. Coming by my office for help, I recommend that you come in, get a group 5 of you, sit at one of our tables out in front of our desk, in front of our offices. You can seat like 5 students there. There's a bunch of tables. Sit there, you work on your homework. You get to a point where you're stuck, come knock on my door, and I come out there and I help you, all right? If you're the only one there, it's one-on-one tutoring, all right? Yes? All right, so I hope this helps. I'm actually going to look at this after the first exam, and I'm going to see like the people who struggled maybe on the first exam. I'm going to look like, did they have time to come see me? Did they come see me? Because I'll keep track of it. If you come see me, I'll log it so that I have a record of you coming in. And so if you don't do well and you had 4 hours a week that you said you could study and come, you could have been there and you never did, that'll be my first question. Why didn't you take advantage of that? Okay. Questions on homework? What is that? Number 51. I'm sorry, I don't have it with me. Did anybody have it with them, the book? I keep on forgetting you have the problem? Okay. My textbook's at home. Number 51. An open rectangular box with a volume of 2 cubic meters has a square base Express the surface area of the box as a function of the length of one of its sides. Okay. Thank you. So I am assuming that everyone had access to that problem. We have a rectangular box with a square base. So it's like a shoebox, right? Shoebox. Now, it said open rectangular box, so we're assuming the top doesn't exist. So it is a shoebox. So it looks something like, here's the front of the box. And then to go three-dimensional, I'm just going to push each of those corners backwards, something like that. And, I mean, depending on how comfortable you are drawing three-dimensionally, is that okay with you? Yeah? It has a square base, means that, what? All the sides? The base is square, which means that the bottom sides are the same. Now, can you read that last thing? Express the surface area as a function of what? The length of the side of the base. So whatever we call the base is what it needs to be the function of. So I'm going to call it L because I had used L up there. I could call it X. So if this is L, because it's a square base, that's L. Everyone okay with that? Now, does that tell me how tall it is? No, I don't know how tall it is. So I'm going to call that H maybe for height. Let's just based off of this picture, can you come up with a formula for the area? Forget that it has to be a function of L. Just can you tell me what the area of a box that looks like this is? So what's the area of that box? Well, you have this front side, right? What's the area of that front side? How wide is it? L. How tall is it? H. So it's just L times H, isn't it? But don't you have another one on the back, the same thing, like that back side? You have another L times H in the back? And isn't this side also L times H? And isn't the one over here L times H? Right there. So all four of those are L times H. Agreed? Four of them. So we have four LHs. Not LH squared, right? Because you're doing L times H plus L times H plus L times H plus L times H. So that is 4 L times H. Now that's just the area of the sides. What else do we have area of? Top and bottom. They said it was an open box though, so we're going to say there's no top. Just the bottom, right? So underneath here, right? Underneath down there, which you can't really see unless you act like you've got special goggles that you can see through the box, right? Would be that bottom there. That would be what? L squared, L times L. Because it would be this length times this length, and they're the same, so L times L. Got that? L squared? So plus L squared. Let's vote. We good with that or not? All right. That's what I want to see. Now, this is definitely an equation that gives us the area, but the area depends on two things, doesn't it? In order for me to be able to tell you what the area is, you have to tell me about the length and the height, don't you? They want you to express the area strictly in terms of length. So we have to be able to eliminate the h from the equation and turn it into something with L. And that's where the other piece of information in the problem comes into play. We know that the volume of this box has to be 2 cubic meters. So what is the volume of that box in terms of the letters that we have there? What's the volume of that box? L times H. right? Length times width times height. So L times H is L squared H. But we know that that has to be 2, doesn't it? The volume has to be 2. That's L squared H. Yes or no? Give me a real quick snapshot of where you're at with that. What now? Solve for H where? On this one, right? Solve for H here, take that answer, and then plug it into the H here, and then everything over here will have L's in it, won't it? So if I solve for L over here, what am I going to need to do? On the left side, solve for L. I said solve for L. I meant solve for H. Apologize. Solve for H over there. What am I going to do to solve for H? Divide both sides by L squared. So H is going to be 2 over L squared. You take that answer, right? This H right here is going to replace this H in this problem right there. So let's rewrite our area. Our area is 4L times H, but we just said H was what? 2 over L squared plus L squared. Now, I'm going to write A of L equals 8 over L plus L squared. So what I've done is I've said now, because my area can be determined with just knowing L, I'm now going to say that A is a function of L. So if I just write A is equal to this, then I'm saying, yes, I can figure out what A is, but it depends on 2 variables, H and L. By writing A of L, I'm kind of stressing to you that it is truly now a function of one thing. I just need one piece of information. I'll give you what area is. And then, is this okay as far as cleaning this up? We're good? Does it talk about domain? Does it want domain at all? It does want domain? Okay. What, should I clarify this? Okay, so multiplication. This is 4L over 1 times 2 over L squared. 4 times L times 2 is 8L. Over the bottom, which is 1 times L squared, is L squared. L over L squared, one of the L's cancels, and you're left with just 8 over L, which is this. Then over here, nothing happens. Now, it wants to know domain, right? What's to know domain? No? Well, let's talk about it anyway. What's the domain of this function? What's the smallest that L could be? Think of it in terms of the geometry of this problem. Could L be 0? No, because then you wouldn't have a box, would you? Right? Also, look at your function. If you try and plug 0 in here, you're undefined, aren't you? So we know that L must be bigger than 0. So I'm going to say something like this. Domain would be something like L is an element of the interval 0, and then how big could it be? How big could this be? It has to have a volume of 2 cubic meters. Any ideas? I may have heard it, but I didn't really hear it. I know some people said something. What do y'all think as far as domain? Is there a biggest value that L could have? Could I make it a box that's 10 meters by 10 meters? If I plug 10 in here, right here, this one. If I plug 10 in here, 10 squared, right, is 100. Divide through, your H would be what? I should do it here instead of here. It'd be 2 over 100, wouldn't it? So even though I have a 10 meter by 10 meter box, it would just be really, really small, right? And it would still hold 2 cubic meters. I could have a box that's, 50,000 meters by 50,000 meters, and it would be like infinitesimally tall. But theoretically, there's no limit to what L could be as far as how big it could be. Understand that? So my domain would be to everything, to infinity. That'll be an important concept later, because what is the goal? We're going to be trying to figure out, like, if I want to manufacture that box, how do I manufacture it to use the least amount of surface, right? The least amount of material. So I need to look at that graph, and when I look at this graph, I'm looking for the lowest point on the graph. And the question becomes, where are we looking on the graph? The whole picture, part of the picture? Well, we'll only look between 0 and infinity, which is like, y-axis on. That's the only place we'll look. Yes? If I ask for it. Mm-mm. No, I'll take any notation that's a acceptable notation. Like, you could do this. Or you could even say, like, L such that, any of that's acceptable. This is all values of L such that L is between 0 and infinity. Sure. Take that. Okay. That's a great question. That'll lead you into the quiz perfectly. So let's do a quiz. Y'all ready? So what I'd like for you to do, are y'all gamblers? Do you like gambling? 50-50. 50-50. Well, we can do a coin flip. We can do group test, a group quiz, or not group quiz with a coin flip. Y'all like to gamble? Do it the way that I intended, which is you do it yourself. Yeah, there's nothing to lose. Yeah. All right. So I have an imaginary coin. No, I don't have any coins. I'll let it be a group quiz. Don't get used to this, though. Okay. This quiz is to give you an idea of what I would have asked you to do on your own today, right now, given what you did for homework and what we've talked about in class. All right. So I'm changing my original idea of today. All right, now because it's a group quiz, it's going to be timed a little bit more stringent. So get working fast. They are, thank you. Need another one? Everyone's turning in their own copy, so Okay, that's time. So at this point, everyone's done. Turn them in. Just hand them all down.
Is the domain part of the grade?
No, just exercise. All right. Any others?
I got nothing.
All right, that it? Okay. Quick little poll here. How many of you felt that you did real well on that? How about real well on the first one? Okay. How about the second one? Okay. How many of you thought that I didn't give you enough time on that quiz? Was that enough time or not enough time? Yes, enough time? Not enough. Was that enough time for that quiz? Okay. All right. Okay, let's see here. Do you think that you would have done worse by yourself on that quiz? That's kind of an obvious question, right? But so there's a couple of things I want to take away from this, all right? That is definitely a type of quiz I would give you, all right? Normally that would not be a group quiz, all right? That would be you on your own. The amount of time I gave you is a factor, all right? Because you may take a little more time to do something, but I would expect you to be able to finish those two problems in 10 minutes easily. Because think of the exam. The exam's going to be long, and time becomes an issue. So maybe, yeah, if you're like, well, I could do that if I had 30 minutes. Well, then you won't be able to finish the exam. So you have to not only get to the point where you're comfortable with the material, but that you can work through it quickly. It especially comes into play for those of you taking Calculus 2. As you move on, the tests become harder because you have to be able to not only produce, but produce quickly. Like, pull it out of the brain fast. That's a skill. That's something that you have to demonstrate. An A student will be able to do it fast, not take 30 minutes to figure out, oh yeah, that's what it was. All right? So we got to address those sorts of things. I'm not going to go through the first one. I'm going to go through the second one. Because this is probably the more important of the two. So this was supposed to say just feet. All right, so it says write the total area of the figure below as a function of its width W if you know the total perimeter, including the inside legs, is 20 feet. So first of all, I want a formula for the area, right? The area of the entire thing is what? LW. L times W. Don't need the dot, but I'm just putting it there, right? Length times width, that's the area of everything. I want this to be a function of W, right? I want W, so I need to get rid of the L. So now I need to use some other information that was given in the problem. What's some other information that was given in the problem? Perimeter is 20. Perimeter including the legs. So let's talk about the perimeter. The perimeter would be this, which would be what? L. This, which would be L, that's two L's. And then it would be 1, 2, 3, 4, 5, 6 W's. If you take the 2 L's and you add the 6 W's, you should get what? 20, right? 20. So I should have that 2L plus 6W must equal 20. What's good about this equation is that this gives me a way of solving for which variable? Because I'm trying to get W here, right? I need to get L replaced, so I'm going to come over here and solve this for L. So move your 6w to the other side. Subtract it on both sides. And finally, divide by 2. And so now we have an expression for L in terms of W. Take this L, replace this L in this equation, and you should have an equation now that just has W in it. So your area will be equal to the L, which is 10 minus 3W. Do I have to have that in parentheses? Yes, because I'm multiplying it times W, so this W will have to distribute through if there's more than one term. And then I could distribute. I don't have to. I'm also going to write A of W. I don't need parentheses. 10W minus 3W squared. And that's what I'm looking for. It is a function of one variable. I can graph it. I can figure out things like, well, how do I make this? How do I build this, right? So that I'm using up all 20 feet, but getting the maximum area out of it. So what do I need to make my width equal to get the most area out? That kind of makes sense? We do that later. Domain. Domain's a little tricky on this one. What's the domain? Well, what's the variable what is our independent variable for this function? W, right? So we're trying to find some restraints on W. What's the smallest W could be? Can't be negative, right? Wouldn't make sense. Can W be 0? I'm going to build this thing, right? It's got to have perimeter of 20 square feet. 20 feet. Could I start building it by making the lengths 10 and 10 and then have a width of nothing? It wouldn't make sense, right? But algebraically, there's nothing wrong with letting W actually be 0. See, in the previous problem, W couldn't, or what was it, couldn't be 0? L couldn't be 0 because that would have been, our box would have been 0, right? Which would have had no volume, and it had to have a volume of 2. Does that make sense? We can still build this where the perimeter is 20, go 10 and 10, but then you don't have anything left to build the rest. So what I'm getting at is that 0 can be included here. It's kind of ridiculous to include it, but we could include it. So 0 could be there. And then how big could W be? What's the biggest it could be? I can't say 20 because if you're telling me that's 20, then that's 20, 20, 20, 20, 20, 20. There's 6 of them, right? 6 20s. You don't have that much, right? It's supposed to be 20 square feet or 20 feet total. Any ideas? I need to build this so I use up all 20 feet of the perimeter. What's the biggest it could be? Pardon? 2, 2, 4, 6, 8, 10, 12. I still have some left over. 4, 4, 8, 12. That'd be too much. 3, 3.5. How about 20 over 6? Yeah. How about 20 divided by the 6 sides? 20 over 6. That would be exactly the biggest it could be. So 20 over 6, which reduces to be 10/3. That would be your domain. W is an element of there. Okay, let's see. Do you understand that or not? We'll have more practice with the domain, okay? That's going to be an important thing because later on what we're going to see is when we're going after a problem, we're trying to figure out these highest and lowest points on a graph. The first thing we're going to ask ourselves is the function restricted to a closed interval? Like this one is restricted to a closed interval, right? Or is it restricted to an open interval like the previous problem? It's somewhere else. Never mind. Right, the last one was 0 to infinity. If it's closed interval like this, we have a certain method we use. If it's an open interval, we have a different method. So you have to identify your domain first before you attack it. So we'll see more. Okay, I'll have to look at the quizzes and determine how I'm going to grade this. You know, I was really hoping everyone would get the first one, and then the second one, I just kind of see where the class is. All right? I'm ready to continue on with our notes from last time. Any other questions before I begin? Comments? You want to talk about our website at all? Any issues here on our website? Canvas, orientation video, syllabus is here. The schedule, this is a printable schedule. It's actually pretty convenient because if you print it out, you can write the homework in. Remember that tomorrow, right, you have a deadline of you're supposed to submit your syllabus confirmation quiz, which is right here. You click on that, it's going to ask you, have you read the syllabus? Do you understand the requirements of the course? Blah, blah, blah. Yes or no. Okay, do that by tomorrow, I think 5 o'clock or something like that. Course videos, those are the videos you're supposed to watch before class. What are these? Class videos. Course videos you watch before class. Class videos. That's what I'm doing right now. Like what I'm recording, right, is going to be posted later on today right here with audio this time. And then the files is where you can find other stuff for the class. Oh, your formula sheet. Didn't I tell you all to try and grab your formula sheet? Print it off. 6 pages. Uh-oh, where is it? Yeah, right here. Formulas. 6 or 7 pages of formulas you're allowed to have. Class notes, course notes. All right, so if you have any questions over that, just let me know afterward. So we had started functions and limits. We had done 1.1. We worked through that last time. And we had pretty much gotten through all this, right? This was the bonus question. We had done the 2 before. And now we'll move on to 1.2, catalog of essential functions. So the only thing here is that being in Calculus 1, I think I might cut the lights just a little bit so you can see these graphs a lot better. It's going to get dark. Please don't go to bed. I'll turn the lights on once I start writing things down here in a minute, but these are the functions everyone should already have familiarity with, all right? All the different power functions. Power meaning x to different powers. If x is raised to the second power, x squared, it's a parabola, right? Both sides of the polynomial go up. X cubed, left side down, right side up. Yes, that's x cubed. X to the 4th, boy, that looks a lot like x squared, right? Goes up on both sides. X to the 5th looks a lot like x cubed. X to the 6th. So you should know what all the different power functions look like. Even powers of x go like that, right? Odd powers, left side down, right side up. Let me ask you a question. If x is greater than y, is x squared greater than y squared? Is that always true or not? No? Can you give me an example of something that would, this is, the way math people think and the way engineers should think is, if you think something's true, you've got to be able to prove it's always true, right? To prove something's not true is easier, because you just have to find one example that doesn't work, right? It's a logic thing. So Mr. Tuck, you're saying you don't think that's true? Okay, if x is 2 and y is -3, is x greater than y? Yes? Is x squared greater than y squared? No. So this is not true, is it? All right, so let me add a condition, because you beat it by making one of them negative, right? So how about this? If I say this all right, so what does this symbol mean? Pardon? Yes, this is the symbol and. So I'm saying if x is greater than y and x and y are both bigger than 0, so now you're not allowed to grab a negative number, then would this be true? What do you think? Let's try something. Give me an x and y that satisfy that. Let's just try it, see what happens. X equals, what, 5 and 2? Is that what I heard? Okay, if you square that, what do you get? 25. Y squared is 4. That works. Does that mean it always works? No, you would have to check every number, right? It's very difficult to prove something's always true. You have to prove it for all cases, which is impossible. So we have other ways we prove things. We just need to see if we can come up with one contradiction. Let me try something else. How about this? X is equal to 1/2. Y is equal to 1/3. Is that x bigger than that y? They're both positive. Square them, what do you get? 1/4, 1/9, right? Yes? It appears that that's true. All right, now, it turns out it is, but we have definitely not proven it is. All right? I wanted you to think about that because now I want you to consider the following. All right? Think about this now. Separate kind of idea. If x is greater than 0, is x to the 4th always greater than, well, I'll make it this way. Is x cubed always greater than x squared? So now instead of giving you two different values and asking you to compare what they are squared, I'm saying here's a value. If you raise it to a power that's bigger than raising it to another, or x cubed, right? 3 is bigger than 2. Will this inequality hold? No? Not all the time or never? Will it never hold or not all the time? So let's see if you can come up with an example where it wouldn't work. What if x is, let's do 1/2 and 1/3 again. Oh, sorry, 1/2. What's x cubed? 1/2 times 1/2 times 1/2 is 1/8. What's x squared? 1/4. So is 1/8 bigger than 1/4? No. Why in the hell am I talking about this? Because I want you to go back and look at this for a second. I want you to look at x to the, this is x squared is the red one, x to the 4th is the green one. Notice that between 0 and 1, x squared is bigger than x to the 4th, isn't it? Between actually -1 and 1, x squared is bigger than or equal to x to the 4th. Once you go past 1, let me zoom out a little bit. Once you get past 1, then the x to the 4th is bigger than x squared. Just pay attention to that little subtlety, because I've seen it later on in like calculus 2. You have to do stuff like this, and you have to graph them. And I see students, and they'll always want to put the x to the 4th on top of the x squared. It's like, no, hold on. Between 0 and 1, it's the other way around. The x to the fourth is below the x squared. Understand? Okay, let's move on. Negative power functions. One of the most important functions in our beginning studies of Calculus 1 is the function x to the negative 1, which is 1 over x. 1 divided by x. Can you plug 0 into 1 over x? No. Right? You get an asymptote. This is the function f of x equals 1 over x. That's what we're looking at right there. Can't plug 0 in, it's undefined. What happens as x gets big? What happens to this function as x gets big? The function gets smaller, right? So let me write it this way. As x gets big, how do I say gets big? It starts to head towards, I don't know, what's a big number? How about infinity, right? As x gets big, f of x gets what? Small. How do we say small? Well, we're saying small 0, right? Does this notation kind of make sense? With this function, if x gets large, the function gets small, starts approaching 0. Yeah? Let's talk a little bit about big and small. On a number line, big numbers are to the right, small numbers are to the left, right? So if I say, give me a very small number, you could say like negative 1 million, couldn't you? That would be small. But then you could also be thinking of small as close to 0, couldn't you? Like 0.000001 would be very close to 0. So we all need to make sure that when we're talking about numbers in this class, our idea of small, we're all like kind of on the same page. We're going to mean like infinitely small to mean like close to 0, as opposed to small that way, which I will always refer to as a large negative number. Understand? So I'm not talking about something way over there on the number line, on the left to the number line. I'm saying a large negative number. If I'm saying small, I'm saying close to 0. No, just the fact that the way the number line works, if I give you two numbers, the smaller one's to the left, right? So if I keep going this way, those are smaller and smaller and smaller numbers, aren't they? So if I say a small number, you might think I mean something way over there. In this class, small means close to 0. All right? Close to 0, something very tiny, like physically like very small if you measure it, the width of it or something. If I want you to be talking about way down there, I will tell you a large negative number. Okay, so that's what's happening as it goes to infinity, right? X goes to infinity, the function gets smaller. What about this? What about as x gets close to 0? Tell me what happens with this function as x gets close to 0. To infinity? It's getting larger, right? But look, if you're coming this way, 0's right here. If I'm walking on this function, I'm approaching 0. I'm going up, right? That's approaching a very, very large positive number, right? Positive infinity. But if I'm on this side and I'm approaching 0, aren't I going down to a very large negative number? So would you agree that if I come in from the left side, I'm headed towards like a negative infinity? But if I come in from the right side, I'm headed to positive infinity? Yes? That kind of makes sense? We're going to spend a lot more time talking about that, but I want you to see it now. Those are going to be called left-sided and right-sided limits later. Left and right limits. All right, here's another function. This is 1 over x squared. What happens as x gets really big? The function gets really small, right? I have the little polling device. I'm going to have to ask you in a second here to take a poll, but I want to make sure that you get this. If I give you a fraction, all right, here's a fraction, and I'm going to tell you that the top of this fraction is a fixed number, and I'm going to tell you that the number on the bottom is not infinity, but it's getting big. Tell me what happens here. The fraction gets bigger or smaller? What? Smaller, right? If a number on top stays the same, the number on the bottom gets big, the fraction gets smaller. Everyone okay with that? Yes or no? You can click it for me. I might have to hide these because I think some people vote yes just because they don't want to be the one person to vote no. But we'll see. It seems like a very ordinary kind of idea, but trust me, I mean, this class is all based upon trying to figure out what's happening when things are doing certain things. Fractions start behaving, numerators doing this while denominators doing something else, and trying to figure out what's happening. Right? So we have to get the foundations down. This is one of the foundational ideas in here. All right, so I can go through the rest of these, but this is 1 over x cubed, 1 over x to the 4th, so on and so forth. Okay, root functions. That's the square root of x. Has a domain restriction, doesn't it? 0 to infinity. Cube root of x does not have a domain restriction. 4th root of x has a domain restriction. Check this out. The 4th root is bigger than the square root between 0 and 1, but it's opposite after 1. Polynomial functions. We could spend 4 weeks studying polynomials. That's what you do in college algebra, right? That's a first-degree polynomial. It's a line. Second-degree polynomials are parabolas. You can have a parabola with 1 x-intercept. You can have a parabola with 2 x-intercepts, right? You can have a parabola with no x-intercepts. Is it possible? Yeah, just shift it up, right? You could have a cubic function. You could have a cubic function with 1 x-intercept, with 2 x-intercepts, with 3 x-intercepts, right? I could go all day. 5th degree polynomials. These things look like roller coasters, don't they? Right? Up and down. And what we did in college algebra is we investigated where these things happen, right? Where are the x-intercepts? Where are the x-intercepts? Where are they happening? Where are they happening? How many of you had to sketch polynomials by hand in college algebra, right? Yes? But what you never did was you never found out where that point was, did you? You never found out where that point was. You never found out where that point was, and then the one that's down here, you never found out where that one was. Well, we will find out where those points are occurring. Then we had the good old rational functions. Remember those? Vertical asymptotes, horizontal asymptotes, slant asymptotes, all that. That was a big mess if you had to do those by hand. So these are all things that we've seen before. We need to kind of bring back in our memory. Because if I'm sitting here, I'm saying, okay, yeah, now we have a cubic function. We all know that the behavior of cubic functions can do this or this. We need to make sure that that's kind of readily available to us. Trig functions, sine, cosine, right? Sine and cosine look the same. Tangent was had these vertical asymptotes, right? Negative pi over 2 and pi over 2. All these trig functions were periodic. Cosecant function, secant. We could draw the secant function by first drawing cosine and then drawing like these little parabola-looking things off the peaks and valleys of the cosine. And of course, you could shift these around and change the amplitude. These are just the basic ideas here. Cotangent. Exponential functions. What happens when you have an exponential function that looks like this? As you go out to the right, it goes up forever, right? Exponentially, up to infinity. But as you come to the left, where does it go? It heads towards 0. If I change the base, that's e to the x. Here's 2 to the x. 2 to the x behaves much the same way. What about 1/2 to the x instead of 2 to the x? It goes the other way, right? So if it's 2 to the x, it's exponential growth. If it's 1/2 to the x, we called it exponential decay. The graph flipped over the y-axis, basically. Then after we talked about the e to the x, right? Here's e to the x. We said, hey, e to the x is 1-to-1, right? It passes the vertical line test and horizontal line test. So it has an inverse. And the inverse of the exponential function is the natural log. There it is. Does the natural log have a domain restriction? Yes. Has to be from where? 0 on, right? Not including 0. So where does it, if you start going out to the right on the natural log, where is it going? So as x goes to infinity, where does the function go? Infinities. It's kind of slow, but it goes, doesn't it? It grows slowly to the left. Do y'all see that or not? Yeah. Okay, what happens as x approaches 0? So you're walking along here, your x value is getting smaller, getting closer to 0. What's your function's value going towards? Negative infinity, right? Negative infinity. That will come up again. Then once we had all the basic functions, you can imagine moving them around, shifting them up, down, left, right, flip over x-axis, y-axis, right? All these different transformations. You know, adding a number shifts it up, subtracting moves it down, adding a number inside, left and right shifts, stretching it vertically and horizontally. I'm not going to show all those. Then we had the algebra of functions. If you have two functions, you can add them, subtract them, multiply, and divide, right? If you had a fifth operation for functions called composition, right? F of g of x. So here are some examples of combining functions. We could add them, subtract them, multiply them, divide them, and then compose them. Example here, these two examples are not that interesting to us in this class because that's just college algebra stuff. What I want to do is this example right here, which is called decomposing functions. If I give you two functions and I tell you to put them together like f of g of x, fog, if you've ever heard that, that's what you did in college algebra. What I want to do now is I want to go backwards. I want to give you a function that looks really nasty. I want you to rewrite it, rewrite this capital M function as the composition of three different functions. All right? Let's do this one. We're almost ready to start Calculus 1. We're just going to finish this, and then we will start Cal 1. All right? This is all just review so far. Not review, but just like getting the brain going again. All right? All right, so I have that function, m of x was sine to the 5th power x squared plus 1. I want to rewrite it so that m of x is actually the composition of f of g of h of x. So when we read this, f of g of h of x, this is a triple composition. It's a function in a function in a function. In a function in a function in a function. So it's really, we could write it like this way. It's f, but inside of f is g, but inside of g is h of x. Right? That's what that means. F, inside F is G, inside G is H. Inside H is X. So your independent variable goes into the H first, right? This function does something to it. That goes into G. G does something to it. That goes into F. So can you look at this, and can you, by looking at this, see that it's actually three basic functions put together? Do you see them? And you always want to start, if you want to figure out what H is and work your way out, you start with the inside and work your way out. So before we work our way out and do all that, I want to make sure we know the order of operations here. If I told you to plug a number in there, like 2, 2 would come in right here first, right? It would get squared. Then you would add 1, wouldn't you? So you'd have 3. Wait, no, sorry, I plugged in 2, right? 2 squared is 4 plus 1 is 5. So you'd have 5, right? Then what would you do? Sine of 5. You would take the sine of 5. And then what would you do? What does that 5 up there mean? Power of 5. So this is really up here. This really means sine x squared plus 1 to the 5th power. This is purely notation. If you see a power right after the trig function, it's saying raise it to this power after you actually do the trig function. So I would do my 2 in here and get my 5, and then I would get my sine of that 5. What's sine of 5? Calculator, right? 5 is not a common angle. It's not anything we know right off the bat. We take that answer, we would raise it to the 5th power. Okay, you okay with me on this? So do you see now that this x squared plus 1 is a basic function? It's a parabola, right? It's just a parabola. And that's a good candidate for my inner function right there. And then what happens to that x squared plus 1? After that part occurs, what's the next function that occurs? The sine. So the sine function would be a good candidate for my g. And then what happens after sine happens? The 5th power, which is up here, right? It's actually the 5th power of all of this stuff, right? But that would be a candidate for f. So watch the way I rewrite this. I'm going to write it, let me do this order. I'm going to put f, then g, then h like this. Yeah. Okay, what did we say the h function was going to be? X squared plus 1. Okay, now what is the g function supposed to do? It's supposed to take sine of something, right? So I'm just going to say it's sine of x. That's it. It's the sine function. What is the f function? It's the 5th power function. So just what? X to the 5th. And that's all. So what happens is this. If you take this h right here and you plug it into g, that x squared plus 1, right, will replace this x. So it would become what? Sine of x squared plus 1. Then if you take that answer and you plug it in for this x, you would get what? Sine of x squared plus 1, all of that to the 5th power, which would be equivalent to capital M. You can check for yourself that this composition works. Now, why is this an important aspect of things here? Well, later on, when we're going to be doing some stuff in this class, we're going to be asked to perform an operation on this function. And when we look at it, we're going to be like, whoa, that's pretty complicated looking. So instead of looking at it from a very complex point of view like this, we break it down into 3 separate, more basic, primitive functions, and then deal with those individually and combine our answer together. So it's kind of like you're taking a problem that was challenging, you're breaking it up into smaller, easier parts, and then putting those answers back together later. That kind of makes sense? All right. Quick poll. Any questions on? Are you good on what I just did? Yes or no? Okay. So that does it for kind of our review of how we got here. I've in the past I've actually started Cal 1 day 1 with 1.3. Just hello, welcome to calculus. Here's the limit. All right. It's possible to do it that way. It's just more recently I've been spending a little bit time on the reviewing part of it. Okay, here we go. You're supposed to watch a video for this before class, but that was not for this class, it's for your next class. We're going to get a little ahead right now. That's never a bad thing to be a little bit ahead. Let's look at this function, all right? What kind of function is this? The graph looks like what? Polynomial, right? I mean, you can see right here, it's what, cubic? What I'd like for us to do is focus our attention on, let's see if I can do this. On the x value of 2, all right? On the x value of 2. You'll see where 2 is right here? Okay, I'm going to get rid of that. There's 2. And I want to know what's happening to the function as I get close to 2. So I'm going to move my little point around here. So the blue on the bottom there is showing the x value, 1.5. The purple, I don't know if you can tell that's purple, is showing the y value. Can you all see that that says 5.625 or something? All right? So what happens as I get closer and closer to 2? What does it look like it's getting closer to? 8? Would you all agree? So as I come in from the left side, the function is getting closer to 8. If I do it from the right side instead, you know, over here it's like negative values. Over here now it's positive. As my x value gets closer to 2, my y value is it goes up above 8, doesn't it? But then it comes back down and it actually becomes 8, doesn't it? But calculus is not about what's happening at 2, all right? We are not going to be interested in this class at all about what's happening at 2. We're interested in what's happening near 2. But before we can do that, we just want to make sure we understand the idea of coming in from the left, coming in from the right. That pretty clear to you? Yes? Look at this function. Different function. This is a piecewise function. Right? We talked about this last class, piecewise. It does something for a while, and then all of a sudden it changes to a different function. So let's look at what happens as we approach 2 from the left. Here we come. Right now, looks like my x values are approaching 2. My y values, what do they look like they're approaching? 8. Now I'm going to go a little bit slower. Getting closer. Yeah, I would agree. It looks like it's getting closer and closer to 8. It's what it visually looks like to me. Does the same thing happen if I come in from the right? No. Comes in, getting closer to 2 with my x value, right? My x's are getting closer to. My y values, they went up here. I'm at 5. Looks like they're going to start coming down again, right? What do those look like they're getting closer to? 4? So it looks like from the left, I'm headed one place, right? My function is headed up to 8. From the right, I'm headed to 4. Totally different values, right? What is happening at 2? Can you tell me what's happening at 2? What's f of 2 here? Let's the function's value there? 8. Why? Why can you tell? Or how can you tell? What's that? There's a hole here at 4 and there's a solid dot up here. The solid dot implies that the function is defined there. Yes? Okay. So this says up here, this kind of reiterates what I just said. From the left, the function's value appears to approach 8. From the right, the function's value appears to approach 4. At 2, the function's value is 8. Now look at this one. From the left, as we approach 2, where's the function headed? Up to 8. As I approach from the right, as I approach 2 from the right, the function's value appears to be headed towards where? Up to 5, and then it's going to come back down to 4, right? It's very much like the last problem, except what's the function's value at 2? It looks like it's wherever that is, right? It's in the middle. So at 2, the function is defined to be 6. Now this one. Here's the function, 2 minus x over x squared minus 4. Here's its graph. It has a vertical asymptote. It has a hole at 2. Why does it have a hole at 2? Yeah, try and plug in 2 into this and you get division by 0. The function's not defined there. I would like to know what happens as we approach 2. Now keep in mind, when I'm doing these demonstrations, I chose to approach 2 because I had to pick something, right? So I stick with 2 pretty much this whole time. I could have picked 3 or 5 or any number. Just 2 seemed to be convenient for me, all right? So let's see what happens as I approach 2 on this function. From the left side, what happens? Well, it's kind of hard to see. Is that kind of hard to see? Looks like I'm approaching like, what? Oops. See, I got to that part where it was undefined, and my computer's like, whoa, what the hell do I do? Right? So there, let me try and go in a little slower. Can you tell what the value is? 0.26, 0.257. Looks like it's headed, I don't know, somewhere like negative 0.25. I know that's very small, but it's not something obvious like the last couple of problems where we could say like 8 and 4, right? What if I come in from the other side? Does it look like it's headed to that same place or not? It's right now, do you see it's negative 0.22? What was it from the other side? It looked like negative 0.25. So as I start coming in here, looks like it's getting closer to like negative 0.25, doesn't it? So it looks like from both the left and right, they're headed towards the same place. But where? What's the actual value? We'll have a way of doing it, all right? Right now, it's just about making the visual connection between what it means to come in from the left and the right. Sometimes it's easy to see it, sometimes it's hard. How about this one? I'm changing it up a little bit. Discuss the behavior of this function at the value x is 0. So here's the graph. If you type this in your graphing calculator, sine x divided by x, and graph it, here's what it would graph. Try and plug 0 in there. What do you get? Division by 0, right? It's undefined. But according to the graph, what does it appear happens as I approach 0? Remember, 0 is right here. As I approach that from the left, what does it appear the value of the function is approaching? 1. Now what happens when I get to 0? Computer doesn't know what to do, right? Division by 0. What happens as I come in from the other side? Same thing, right? Approaching 1. How in the hell would you know that without the picture? How would you know that if I plug 0 in here, well, it's undefined, but how would you know that if you plug something in close to 0, you're going to get something close to 1? See what I'm getting at or not? Let me ask you, do you see what I'm getting at or not? Okay, there's some no's. Good. All right. So then we'll go back to this one. If I give you this picture, you can tell that from the left and from the right, they look like they're headed towards the same place. Yes? It appears to be about negative 0.25. That's what it looks like it is. My question, though, is how would you know that without that graph? Right? How would you know that that's the way it's behaving? On the other one, again, sine x over x, you can't plug in 0. Right? You're not allowed to. So how would you know that as you get close to 0, it's getting close to 1 without having a graph? How would you know that? I mean, I'm not expecting you to know the answer to how you would know that, but do you see where the issue is here? Like, how can you determine the behavior of these things without a visual understanding of them? There's not an easy way yet, and that's what part of this calculus course is about, is being able to determine what these values are without looking at a graph, by just doing an analysis of it. Okay? Let's see, I don't want to push too far here. Yeah, let's just finish this off right here. There's only a we'll finish this last one right here. And then I'll talk about some other stuff to help us out, to try and clarify a little bit more what I'm talking about here. Look at this one right here. Sine of 1 over x. Let's talk about what's happening at 0. Can you plug 0 into this function? 1 divided by 0? Undefined, right? Can you tell me what's happening near 0? So as you're getting closer to 0, what's happening? Well, let's see. According to the graph, let's start coming in here. And then what's happening here? Just going along, it goes up, and then starts going back down, and then it goes back up, and then back down, and then back up, and then back down, and up and down, up. Just oscillating, right? And you know how you see how it looks all like crammed in there? It's actually because it's oscillating infinitely many times. And so this function is just going crazy near 0. It does not know how to behave. It's trying to go back and forth between negative 1 and 1 because it's a sine function, but because this is becoming undefined, it's like jumping back and forth. So could you say easily, by looking at this graph, could you tell me where it's headed as you come in from the left? No, I mean, it's going back and forth. How about from the right? Same thing, right? Just going back and forth. And so there is no answer. It's coming from the left and right. It's not headed towards anything in particular. Like everything else before this, left and right, it was headed somewhere, wasn't it? Here, it was headed left and right. It was headed to one particular value. Here, left side was different than right side, wasn't it? But they were going somewhere. This one, just all hell broke loose there, right? It's just chaos, really. It's a chaotic point there. Okay, so I think that's a good place to stop. Let me go to a different slide and just talk a little bit about that one problem we had here. Where was it? This one here. 2 minus x over x squared minus 4. All right, I'm just going to write this one down. And we said already that when you try and plug 2 in, what happens? 0 on the bottom, right? And top. So you get, if you try that, you get 0 over 0, don't you? Which is undefined. It's undefined. So the question is now, what happens if you don't plug 2 in, but plug in something close to 2, and what would you get? So imagine coming in from the left and from the right and plugging them in, seeing if you can figure out what the value would be. So can somebody give me a value that would be close to 2 from the left? So here's 2 on the number line. My graph was doing something, right? Can somebody give me a number that's really close to 2, but to the left of 2? 1.9? That would be on the other side of 2, right? From the left side, let's do that first. 1.9, right? So from the left, if I let x be 1.9 and just plug it in and break out my calculator, I would get what? 2 minus 1.9 divided by 1.9 squared minus 4. Yes? So someone grind that out for me. Negative what? 0.1. Oh, okay, negative 0.1 over 0.2, which is what? Are you getting that? I better break out mine. You got negative 0.5? Okay. Now wait a minute. Hold on. We said that on this graph when we came in from the left, didn't we say that it was getting really close to? What did we say it was getting really close to? It looked like negative 0.25 or something like that. I can actually put in 1.9 right there. We should be getting. Maybe that's all. Yeah, I think the calculation is wrong. Okay, let me see. 1.9 squared. Okay, here we go. You should have on top 0.1. 2 minus 1.9 is 0.1. When you square 1.9 and subtract 4 from it, you should get negative 0.39. When you divide those, 0.1 divided by negative 0.39, you should get negative 0.25641, something like that. Yeah? Now, 1.9 was close to 2, but you could get even closer, couldn't you? What would be even closer than 1.9? You could do 1.99, couldn't you? That would be even closer. I'll do that one just real quick to see what would happen. We would get, if I plug that in, we get 0.01 over, let me do this real quick, 1.99 squared, take away 4, I get negative 0.0399, and if I divide, I get negative 0.250627. That's what I would get. Looks like it's getting closer to what? Negative 0.25641, negative 0.250627. Maybe the next one would be even closer to negative 0.25. Now, if we switched it up and we came in on the other side of 2, which would be up here to the right, coming in from the right, this is where we could use 2.1, right? What would happen if you plug in 2.1? (2.1 minus 1.9), I'm sorry, did this wrong. 2 minus 2.1 over 2.1 squared minus 4. What do you get? 2439. Good. Good enough. So that looks like it's pretty close to negative 0.25. How could I get even closer than 2.1? 2.01. Even closer? 2.001, right? And what we could do is start getting some behavior, what's happening left and right. But this sucks, right? To do it this way sucks. And that's not the point. All right? The point is not to make a table and try and figure out what's going on. The point is to try and figure out a way of doing it without having to do something like this. So this is just to convince you that if we do start letting points get closer to 2, it confirms what we saw geometrically from the picture. But let's act like we don't have a picture, like we never made a table. Let's just start the problem from scratch and try and figure out what's happening at 2. All right? So starting this thing over, here's our function, 2 minus x over x squared minus 4. What I notice here is that when I try and plug in 2, right, when we tried to plug in 2, we said it was 0 over 0. Okay? That is something that from now on, when we see 0 over 0, we're actually going to get excited about it because that means we're going to be able to do something with it, hopefully. So I wonder if you noticed that right off the top of this, the bottom was a difference of squares. Yes? And then we can cancel a factor here, can't we? Almost. They're off a little, aren't they? Yeah, this top one up here is almost this one right here, but they're off by a sign. So we factor negative 1 out of the top to make them match each other. Factor negative 1 out of the top. How does that change the numerator there? How does it change this? Flips it. So how do you want me to write it? Negative 2 plus x, or you want me to say x minus 2? X minus 2. And then on the bottom, x plus 2, x minus 2. And now we can cancel these factors. Quick poll. You okay with me on this? And I talked to my 1414 class about exactly what we just did right here today. There's something very subtle about this cancellation. When you cancel something like this in a rational expression, you're almost signing a little waiver on the side that says, I'm allowed to cancel this so long as I never let what? X ever be 2. Because by eliminating that, you're saying that this statement or this expression, this function up here is equivalent to negative 1 over x plus 2, right? That's what you're saying? But these two are not equivalent. This one, can you plug 2 into this? Yes. Can you plug 2 into that? No. They are not the same. So this cancellation is true, right? This is okay if x is not 2. Yes? So let's see now if we can recover what the hell we're here talking about right now. We did this algebra here. We got this down to this, but we said this is only true as long as I don't let x be 2. And we were trying to figure out what happens as x got what? Close to 2, right? Close to 2. So can I look at this if I want to talk about what happens when x gets close to 2? Yes, because I'm saying I can't use this if x is going to be 2, but I'm saying what's happening when x is close to 2. So tell me what would happen if I plug a number in here that's really, really close to 2. What would the bottom be really, really close to? 4, right? Wouldn't this be really, really close to 4 on the bottom? And what's negative 1 divided by 4? Negative 0.25, isn't it? Which is what it's approaching. So the closer and closer and closer x gets to 2, the closer and closer and closer this gets to 4, the closer and closer this whole thing gets to negative 0.25. Do you see that? All right. We're going to spend a lot of time on this. It's just to get us going. I'm trying to get us ahead a little bit right now. Last idea. I know you only have 2 minutes, but talk about this real quick. Closeness. So I'm talking about being close to 2, right? Getting near 2, getting close to it. 1.9, 1.99, right? There's kind of a problem with the idea of closeness. What's the problem with it? What's that? It's not exact, right? I mean, your idea of closeness and my idea of closeness are two different things, possibly, right? Am I close to? Am I close to you, Mr. Tuck? Are we close right now? We're not very close. Mr. Tuck, are we very close? This space right here seems like a lot of space. Yes. To you, this isn't close? All right, so am I close to SeaWorld? All right. All right, relative to the sun, am I close to SeaWorld? Yes? Relative to the sun? So if SeaWorld is close to me relative to the sun, then we're like really, really close, right? So do you see that close doesn't make a whole lot of sense in math? Like, you can't just say it's close. I mean, if you say 1.9, you could say 1.9 with 29s and be satisfied that that's close to 2. Does that make sense? But then I could come in here and say, no. To me, being close to 2 is 1.9 with a billion nines. And then Mr. Tuck comes in and says, no, 1.9 with a billion raised to the billion nines. You never run out of nines, right? I mean, there are infinitely many numbers between any two numbers. That's a big point here. You pick any two numbers on the number line, any two. There are infinitely many between them. Infinitely many. So many you can't count. You can't even start counting them. All right? So what happens, who's my math majors? Any math majors in here? Okay, so I'd just be talking for no reason then. In math majors study calculus from a theoretical point of view, because in a Cal 1 class like this, we say it's getting close to 2 from both sides, getting close, but we kind of say, just don't ask me really what close means at this point. And then when you get into the theoretical math, you actually have to come up with a precise definition of closeness, what it means. So I just wanted to mention that because I think there's some number sense in this that's important. Infinitely many numbers between any two numbers. That's kind of a weird concept. All right, your homework, I have to send it in an email. Did y'all get it okay last time with that email? Okay, I'll do it again. Make sure you turn in your clickers. If these lectures seem a little bit kind of scattery right now, don't worry, it'll all come together once we start having like point A to point B is where we're going every day. All right. Have a great weekend.